In this video, we solve problem 6.2.21 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to solve the given initial value problem. We have a homogeneous linear constant coefficient differential equation, and then we have three initial conditions. The differential equation happens to be third order. And so the best way to solve this really is to just solve the differential equation first, find the general solution, and then we will use these three conditions to give us three equations and three unknowns. Since this is a third order equation, we know that the solution is going to have the form C1y1 plus C2y2 plus C3y3. It's just a linear combination of the three linearly independent solutions to that differential equation. So we've got three constants in that solution. To find the values of those three constants, we're going to use these initial conditions. So that's the plan. Let's start by solving the differential equation. Since it's a constant coefficient differential equation, we'll start by letting y equal e to the mx. Because derivatives of exponentials give us other exponentials, and if we choose the right exponential, all of these exponentials, when multiplied by constants and added together, will cancel and we'll just get 0. Since it's a third order equation, we're going to compute y prime, and then y double prime, and y triple prime. And then we'll substitute those expressions into the differential equation, assuming that y equals e to the mx is a solution, and that will give us an equation that m must satisfy if y equals e to the mx actually is a solution. The derivative of e to the mx is e to the mx times the derivative of the inside, that's just an m by the chain rule. We take the second derivative, bring the m down, and then you say, what's the derivative of e to the mx? It's e to the mx times the derivative of the inside. That's going to give you another m. M times m is m squared. Bring the m squared down. Take the derivative of e to the mx. You get m times e to the mx again. So you have m cubed. Now we're assuming that this is a solution to the differential equation. So we should be able to substitute these values into the differential equation and get an expression that m and e to the mx must satisfy if this is truly a solution. So we'll substitute into the equation. We want y triple prime minus 4 times y double prime plus 12 times y prime minus 16 times y, which was e to the mx. We want that to be 0. So if e to the mx satisfies the differential equation, then this equation must be true. So we can factor out the exponential. And we know this exponential is never 0, so that means that the polynomial must be 0. Or in other words, the values of m that satisfy this polynomial equation are the values of m that caused e to the mx to be a solution of the differential equation. So we just need to find the m's that satisfy this. Then we know the functions that will cause the differential equation to be satisfied. And when we have three linearly independent functions, we can multiply them by constants and add them together, and that's going to give us the general solution. Okay, now with something like this, if it's possible to factor, we should always factor. If it's not possible to factor, we can always use possible rational roots. This is called the characteristic equation of the differential equation. We want to factor the characteristic equation now so that we can solve it. Now, there's no guarantee this is going to work, but I might say take these two terms and these two terms and see if they have anything in common. Well, m cubed and 4m squared have a factor of m squared in common. And then I say m squared times what will give me m cubed, well, just another m, and m squared times what will give me a negative 4m squared, so we'll have a negative 4 there. And then over here, we want to factor something out. The 12m and the 16 have a factor of 4 in common as well. 4 times 3m would give me 12m, and 4 times negative 4 would give me negative 16. So this is equivalent to this, but it actually doesn't help me, because when I look at this and this, they don't have anything in common. So factoring by grouping was my first choice. Said, maybe you can just factor by grouping. But it turns out that factoring by grouping is not going to work. It's not going to help me this time. So let's try something else. Let's go back to our cubic polynomial here. If all else fails and it's not obvious how you should factor the equation, I suggest using possible rational roots. So the possible rational roots of a polynomial equation are given by quotients of the factors of the constant term. In this case, that's negative 16, divided by the factors of the leading coefficient. And of course, there's nothing there, so the leading coefficient is an implied 1. So we want factors of 16, negative 16. Now plus and minus 1 and plus and minus 16 will work. Plus and minus 2 and plus and minus 8. Plus and minus 4. 4 times 4 is 16. And then we want to divide all of those by plus and minus 1. That's giving us this list. We have 1, 2, 3, 4, 5. But then this could be positive or negative. So we actually have 10 possible rational roots here. 1, 2, 4, 8, and 16. Negative 1, negative 2, negative 4, negative 8, and negative 16. Now, if you're saying to yourself, oh, I have to check all 10 of those to see if those are roots. Well, hopefully not. You don't have to check all 10. But at least, we're guessing. We're trying to find a value of m that causes this equation to be 0. That's called a root of the polynomial equation. It's also called a 0 of the polynomial. We can find that 0 by just randomly guessing m values. But if we try m equals 3, that's definitely not going to work, because m equals 3 is not on this list. The benefit of using possible rational roots is it narrows down that infinite set of possibilities to a finite number of possibilities. So we've got 10 possible rational roots for this equation. Let's see what will work. Notice that we've got a positive term and a negative term and a positive term and a negative term. So chances are that there's a value for m that we can substitute in here so that the positive terms and the negative terms cancel out. M equals 1 I don't think will work. That'd be 1 minus 4 plus 12 minus 16. 12 minus 16 is negative 4. Negative 4 and negative 4 is negative 8 plus 1 is negative 7. So that's not going to work. But I wonder if m equals 2 will work. So I'm going to try m equals 2. I want to see if m equals 2 is a root of this polynomial. So we'll just take it, we'll cube it, substitute it in for m. We'll see if it works. So I've got 4 times 4 is 16 there. Okay, so we have 8 minus 16 is negative 8, and 24 minus 16 is positive 8. That does work. So m equals 2 is a 0 of the polynomial, or it's a root. That means that m minus 2 is a factor of the polynomial. So this can be written as m minus 2 times some quadratic function. To find that quadratic function, we want to take this polynomial and divide by m minus 2. We will use synthetic division. Before we do that, let me label what we've done so far. Possible rational roots. Yes, try, you're just going to try values from the list until you find one that gives you a root. And when I say it gives you a root, it's a value of m that satisfies this equation. So you plug in the m value and you get 0. Okay. Then after you've done that, we want to divide out that m minus 2 factor so we can find the quadratic polynomial that's left over. We had a cubic polynomial, m cubed minus 4m squared plus 12m minus 16, and we want to divide by m minus 2. That's going to be equal to q of m. And we're going to use synthetic division to do that. Okay. So the way we do synthetic division is we take that divisor and we set it equal to 0 and solve for m. So in other words, you're finding the 0 or the root that corresponds to that factor. So m minus 2 is 0 when m is equal to 2. And then you list the coefficients of this polynomial over here. You need the polynomial to be in descending powers of m, starting with the highest power and then decreasing all the way down to m to the 0. Now this one already has an m cubed term, an m squared term, an m to the first term, and then there's no m's there, that's m to the 0. So we're already in the right form. The coefficients are just 1, -4, 12, and -16. But if there was a missing term, we'd have to add a placeholder. Like let's say there was no m squared term, we'd have to add in a 0m squared, and then we'd have to put a 0 right there. This time we've got all the terms, so we just list those coefficients right there. Then you bring this first number down, you multiply, you get 2, then you add. Then you multiply, we get -4, and then we add. We multiply, we get 16, and then we add, and that's good. When we divide by m minus 2, the remainder should be 0. Since the remainder is 0, we know that m equals 2 is a root, and therefore m minus 2 is a factor, and the coefficients of the quadratic polynomial that are left that is left when you divide this out are right here. So this was cubic, we divide by a linear polynomial, so the power is going to go down by 1. So this is the coefficient of m squared, because 3 minus the 1 is giving us 2. So this is going to be an m squared term. This corresponds to the m term. That corresponds to the constant term. So q of m is 1m squared minus 2m plus 8. Or in other words, our original polynomial, which we were trying to factor, is equal to m minus 2 times this polynomial. And we want that to be equal to 0. And then this polynomial can be factored further. I need two numbers that multiply to give me positive 8 that add to -2. Ooh, I don't know if that's going to work. If that was a -8, that would work, but it's not going to work. This is an irreducible quadratic. So this is what we'll do. Sorry about that. I'll set m squared minus 2m plus 8 equal to 0 and solve that equation by completing the square. So the first thing we'll do is we'll get rid of the 8 by subtracting 8 from both sides. Then if our coefficient of m is a 1, and it is, the number in front of the m here is called b. This is the coefficient of m squared is a 1, and it is. Then we call this number b. You want to take half of that and square it. -1 times -1 is +1. Add 1 there and add 1 there. So then this is a perfect square. Of course, negative 8 plus 1 is negative 7, so you simplify the right-hand side. Two numbers that multiply to give us 1 that add to negative 2 are negative 1 and negative 1. So you have m minus 1 squared equals negative 7. And then if you take the square root of both sides, don't forget the plus or minus on this side, you have m minus 1 equals plus or minus square root of 7 times I, because the square root of negative 7 is square root of 7 times I. Add 1 to both sides, and you have 1 plus or minus square root of 7 times I, and that's two different roots. So our cubic polynomial has 3 roots. The first root comes from setting m minus 2 equal to 0. If we add 2 to both sides, we get this. So I'll say m1 is equal to 2. And then I've got 2 more roots that come from setting this quadratic polynomial equal to 0. So if that's m1, I'll call these m2 and m3. And I'm thinking of this as alpha plus or minus beta I. Alpha is equal to 1. Beta is equal to square root of 7. And now we've got all these pieces, and we can put them together to come up with our general solution. Okay, so we found Q of m using synthetic division. We write the characteristic equation in factored form. And then you just solve for m1, m2, and m3, and we did. And then once you have m1, m2, and m3, you can state y1, y2, and y3. So m1, that's just a distinct real root. So the solution that goes with that is e to the m1x. So it's e to the 2x. Now for complex conjugate roots, we would have exponentials with complex exponents. Those exponentials with complex exponents are equivalent to solutions involving sine and cosine. So as we've discussed before, if you have a complex conjugate pair given by alpha plus or minus beta times I for your roots of your polynomial equation, y2 is e to the alpha x times cosine of beta x. So in our case, alpha is 1, so this is e to the x. Beta is square root of 7. And the second solution looks just like it, but instead of having a cosine, it has a sine function. So we'll have e to the x times sine of square root of 7 times x. And then the general solution of the homogeneous linear differential equation with constant coefficients is y equals c1y1 plus c2y2 plus c3y3. So that's c1 e to the 2x plus c2 e to the x times cosine of square root of 7 times x plus c3 e to the x times sine of square root of 7 times x. Okay. And the interval of existence is all real numbers. So all of these functions are well defined for all real numbers x. Now, if we were just asked to solve the differential equation, we would be done. That would be our answer. But now we have to find the values of C1, C2, and C3 that cause this equation to satisfy these 3 initial conditions. We need y of 0 to be 1. We need y prime of 0 to equal 0 and y double prime of 0 to equal 0. In order to make that happen, we're going to need to compute the first derivative and the second derivative of y, and we'll replace x with 0 and y with 1. We'll replace x with 0 and y prime with 0, and we'll replace x with 0 and y double prime with 0. So we're going to have an equation for y, an equation for y prime, and an equation for y double prime. When we make those substitutions, we're going to have 3 equations and 3 unknowns involving C1, C2, and C3. And we can solve that however we want. Since it's a linear, or it's going to be a linear system of equations, we're just going to solve by elimination. You're just trying to get rid of the c's one variable at a time, as you'll see. Okay, so first, in order to set up the 3 equations and 3 unknowns, we need to compute y prime and y double prime. Okay. So y prime is this, the derivative of this piece. Bring your c down. Derivative of e to the 2x is e to the 2x times the derivative of the inside, which is a 2. Over here, bring your constant down. Well, actually, let's do it this way. Thinking of this as the product. This is my first function, and this is my second function. We'll have derivative of the first, which is e to the 2x, or sorry, excuse me, c2 e to the x, times the second, plus the derivative of the second. Derivative of cosine is negative sine, times the derivative of the inside, that's going to be a square root of 7, times the first, which is c2 e to the x. Okay, so that's derivative of the first times the second plus the derivative of the second times the first. Okay, now we're going to do the same thing over here. Here's our first function and our second function. We have derivative of the first, derivative of a constant times e to the x is a constant times e to the x, times the second, plus the derivative of the second. Derivative of sine of square root of 7 times x is cosine of square root of 7 times x, times the square root of 7. It's the derivative of the inside. It's the derivative of the second, times the first. Okay, so we've got 2c1 times e to the 2x. And then over here, we can combine those that involve sine and those that involve cosine. So I've got an exponential times sine right here and right here. So let's factor out the constants. We've got c3 minus square root of 7 times c2 times this exponential times sine of square root of 7x. That's taking care of these guys. Taking care of this one, and this one. And now we want to group the cosine terms. For the cosines, we have c2 times this exponential times cosine plus square root of 7 times c3 times the exponential times cosine. Okay, that's a lot, but that is our y prime. And now we need to compute y double prime. And again, what we're doing is we're preparing to set up 3 equations and 3 unknowns. Since our initial conditions involved y prime, and y double prime, we need to compute y prime and then y double prime for our general solution. So remember, this is our y prime. Now we're taking the derivative again. 2c1 is a constant, so you bring that down, and then you multiply by the derivative of e to the 2x. Derivative of e to the 2x is 2 times e to the 2x. Now here I've got a constant times this product, so I think I'll bring my constant down, and then I'll use the product rule for the rest. We have the derivative of the first, which is that exponential, times the second, plus the derivative of the second, square root of 7 times cosine of square root of 7x, times the first. Now, it's a little bit hard to tell what I wrote there. That's a square root of 7 times the x, and the x is not under the radical. Okay, so that's that. And I'm going to leave some space because I'm going to distribute a little bit. And then we'll have this constant. And then we'll use the product rule here. Derivative of the first times the second plus the derivative of the second. Derivative of cosine is negative sine times the derivative of the inside times the first. Okay. So now you want to distribute where you can. And I'm thinking of this as, I know it's not a monomial, but I'm sort of thinking of it as a monomial. I'm taking that whole thing and I'm distributing it to that term and then to that term. So those two pieces. And then I'm taking this whole thing and I'm distributing it to that term and that term. Okay. So we end up with 4c1 times e to the 2x plus this expression times e to the x times the sine function. And then we have this times this square root of 7 times the cosine function. So I'm going to distribute that square root of 7 to here. Square root of 7, we'll have square root of 7 times c3, and then square root of 7 times a negative square root of 7 is a negative 7 times c2 times that exponential times the cosine function. And then down here, we've got c2 plus square root of 7 times c3 times the exponential times the cosine function. And then here, we're taking this and distributing it to this. So I'm multiplying each of these expressions now by square root of 7, or negative square root of 7. So we'll have negative square roots of 7, c2. The negative times a negative is going to make that a positive 7 times c3. And that's going to be an exponential times sine. Okay. Now we could simplify more, but we don't really need to. A lot of this is going to simplify when we substitute in x equals 0, because we're substituting in x equals 0 to y and y prime and y double prime. And then we're setting the results equal to 1, 0, and 0. And that's going to give us 3 equations with 3 unknowns. Okay. That's the plan. So there is our y. We want to evaluate that at x equals 0 and set the result equal to 1. Okay, so we have y of 0 equals 1. That's the same as saying that when x equals 0, y is equal to 1. So let's go to our function y. That's this function right here, and evaluate it at x equals 0. So we're going to have y of 0 equals c1 times e to the 2 times 0 plus c2 times e to the 0 times cosine of square root of 7 times 0 plus c3 times e to the 0 times sine of square root of 7 times 0. So evaluate everything at 0. And then simplify where you can. E to the 0 is 1. So this first piece just becomes c1 times 1. So that's just a c1. Over here, we have an e to the 0, which is 1, times a cosine of 0, which is also 1. So we have c2 times 1 times 1. So it's going to be plus c2. And sine of 0 is 0. So I've got c3 times 1 times 0, which is, of course, 0. We're setting this result equal to 1. This would be y of 0, no matter what the initial condition was. This time they're telling us that when x equals 0, y of 1 is equal to 1. So we know that whatever c1 and c2 are, c1 plus c2 has to equal 1. So this is our first of our 3 equations and 3 unknowns. To get the other 2 equations, we use the other 2 initial conditions. The next initial condition said that y prime of 0 is equal to 0. So that means this: when x is 0, y prime, that function, has to be equal to 0. So we will evaluate y prime at 0, and y prime has this expression here at the very bottom. I just want to cover up everything else so that you're not distracted by what you see there. All right, so there's your y prime. We're substituting in x equals 0 here. So we've got 2c2 times e to the 2 times 0 plus c3 minus square root of 7 times c2 times e to the 0 times sine of square root of 7 times 0 plus c2 plus square root of 7 times c3 times e to the 0 times cosine of square root of 7 times 0. Evaluate all that at 0. And simplify where you can. Okay, e to the 0 is 1. So all of these guys are 1. Sine of 0 is 0. Cosine of 0 is 1. So this ends up being 2 times c1 plus something times 1 times 0. So that whole thing is gone because anything times 0 is 0. And then we just end up with that piece there. And we're setting that result equal to 0 because we're told that when x equals 0, y prime is equal to 0. So we set this one equal to 1 because when x equals 0, y equals 1. On this one, we set this equal to 0 because when x equals 0, y prime equals 0. That's our second equation. We've got 2 equations with 3 unknowns now. We need 3 equations and 3 unknowns in order to find c1, c2, and c3. The last one comes from y double prime. We were told that y double prime of 0 equals 0. So that means that when x is equal to 0, y double prime is equal to 0. And y double prime was this expression right here. So I am going to almost look right up here and evaluate. We have 4 times c1 times e to the 2 times 0. So that's just going to be a 4c1. And then for these sine functions, sine of 0 is 0. So that's going to be gone and that's going to be gone. The only parts that are going to be left are this part and this part. Because when we evaluate this at 0, we've got sine of 0, which is 0. So we'll have something times 0, which is 0, something times 0, which is 0. And then here, we've got something times e to the 0, which is 1, times cosine of 0, which is 1. So it's just going to be this expression times 1 plus this expression times 1. So what we end up with is square root of 7c3 minus 7c2, that's this piece here, plus c2, plus square root of 7c3. Okay, I didn't show all of my work that time, but I hope that just talking through it was enough. Let's simplify as much as we can. Got 4c1 there, and I've got negative 7c2 plus 1c2 is negative 6c2. And I've got one of these and another one of these, so I've got 2 of those. And we need that to be equal to 0. So we're going to set that equal to 0. All right, that's great. Now we've got 3 equations and 3 unknowns. So our equations are these. c1 plus c2 has to be 1. And 2 times c1 plus c2 plus square root of 7 c3 is equal to 0. And we could take this one and divide it by 2. If we divide by 2, we'll have 2c1 minus 3c2 plus square root of 7c3 equals 0. Okay, those are our 3 equations and 3 unknowns. Now we just have to solve this system of 3 equations and 3 unknowns. Okay, so here's the idea. When you have a system of 3 equations and 3 unknowns, you really just want to get it down to a system of 2 equations and 2 unknowns. And then you'd like to get it down to a system of 1 equation or a single equation with 1 unknown. You eliminate 1 variable at a time until you just have 1 equation that you can solve. Once you have that value, you can use it to find the next value, and you can use those last two values to find the first value. So it's just this process of taking three equations and three unknowns down to two equations and two unknowns, and then getting one equation and one unknown, and then back substituting until you find all the C's. That's the plan. So the question becomes like, how do you want to do it? How do you want to write this as one equation or two equations and two unknowns? Which variable do you want to get rid of? I kind of want to get rid of the C3s because they've got this square root of 7 coefficient. So that's kind of unpleasant. I mean, not too bad, but it'd be nice just to not have to deal with square roots of 7 in our equations. So I think I'll use equation 2 and equation 3, and I will put these two together by subtracting. If I take this first equation 2, and I subtract equation 3, the C3s will disappear. The C1s will also disappear. So turns out this time, taking equation 2 and subtracting equation 3 is going to get us one equation involving C2. But let's see how that works. Now that's not usually what happens. It just happens to happen that way this time. So we just leave equation 2 alone. And then you want to take equation 3 and multiply it by -1, and then you want to add them together. So if I multiply this equation on both sides by -1, I have I'm just going to change the signs on this side. And of course, the opposite of 0, -1 times 0, is just 0. Remember, whatever you do to the left-hand side, you have to do to the right-hand side, but with 0, it looks like nothing has changed. Then we'll add everything together. These happen to reduce and these happen to reduce. So we get 4 times C2 equals 0. And then if we divide by 4, ta-da, turns out that C2 has to be 0 in order for this to work. Great. Now that I know that C2 equals 0, I can use the first equation to find C1. So we're going to, let's see, what did we do? We did equation 2 minus equation 3. We did this to eliminate C3. At the same time, we happened to eliminate C1. Whoops, C1. So we ended up with one equation and one unknown, so we solved for C2. And now that we know what C2 is, we've got a system of two equations and two unknowns there. The easiest variable to find next is C1 because this equation only involves C1 and C2. So let's substitute C2 equals 0 into the first equation. So we've got C1 plus C2 equals 1. And we know that C2 is 0 now. So that means that C1 must be 1. Oops, I wrote 0. Must be 1. And now, since we know what C1 is and we know what C2 is, we can substitute that, C1 and C2, into either equations 2 or equation 3 and solve equation 2 or equation 3 for C3. I'm going to choose equation 2 there. So let's substitute C1 equals 1, C2 equals 0 into equation 2. So this was our original equation 1. We substituted there and we got C1. And then down here, we want to go to equation 2. And we want to solve for C3. C2 is 0. C1 is 1. So we end up with 2 plus square root of 7 times C3 equals 0. So C3 is equal to negative 2 divided by the square root of 7. You can rationalize if you want to, you don't have to. But if you want to, if we do rationalize, we get negative 2 times the square root of 7 over 7 for our C2, or excuse me, our C3. Okay, so we had 3 equations and 3 unknowns. We used elimination and substitution to find C2 and C1 and then C3. Those are our values. Now that you have C1, C2, and C3, you want to substitute those into the general solution to find the particular solution. Okay, so our general solution was here. We had y equals c1 e to the 2x plus c2 e to the x times cosine of square root of 7 times x plus c3 times e to the x times sine of square root of 7 times x. And now we know that c2 is 0 and c1 is 1 and c3 is negative 2 times the square root of 7 over 7. So the particular solution is this with that substitution there. So we have y equals e to the 2x minus 2 times the square root of 7 over 7 times e to the x times sine of square root of 7x. And that will work on the interval from 0 to infinity. Okay, so that process at the end where we were solving the 3 equations and 3 unknowns, it's not actually the best example of that process, because most of the time when you take those 3 equations and 3 unknowns, you want to get it down to 2 equations and 2 unknowns. This time it just so happened that using equations 2 and 3 got us down to 1 equation and 1 unknown from 3 equations and 3 unknowns pretty quickly. So then the method is a little bit less organized. But generally, you want to go from 3 equations and 3 unknowns to 2 equations and 2 unknowns, 2 equations and 2 unknowns to 1 equation and 1 unknown. And then once you have that 1 unknown, then you substitute into the 2 equations and 2 unknowns to find the other one. And then once you have these 2, then you substitute into a 3rd equation to find the 3rd variable, the value of the 3rd variable. So that's kind of what we did here. We just quickly, very quickly got to C2 equals 0 because the C1 and the C3 happened to cancel out. Okay, so that is our example of solving an IVP. First, you find the general solution by letting y equal e to the mx. You substitute, you factor, use possible rational roots if necessary, and then you get your general solution, c1y1 plus c2y2 plus c3y3. And then in order to use the initial conditions, which were right here, to find c1, c2, and c3, we needed to compute y prime and y double prime. Then we replace x with 0 and y with 1. Then we replace x with 0 and y prime with 0. And we replace x with 0 and y double prime with 0. And that's going to give you 3 equations and 3 unknowns. You solve that system of 3 equations and 3 unknowns using whatever methods you want from pre-calculus. A little bit of a process, but it's not too bad. It's based on all the skills that you already have from your prerequisite classes. So let me know if you guys have any questions about that.